This is the Earth, as it looked 90 million years ago. Geologists call this period the Late Cretaceous. It was a time of extreme global warming, when dinosaurs still ruled the planet. They went about their lives secure in their place at the top of the food chain, oblivious to the changes taking place around them. The continents were drifting apart, opening huge rifts in the Earth's crust. They flooded, becoming seas. Algae thrived in the extreme heat, poisoning the water. They died and fell in their trillions to the bottom of the rifts. Rivers washed sediment into the seas, until the organic remains of the algae were buried. As the pressure grew, so did the heat, until a chemical reaction transformed the organics into hydrocarbon fossil fuels, oil, and natural gas. A similar process occurred on land, which produced coal. It took nature about 5 million years to create the fossil fuels that the world consumes in 1 year. The modern way of life is dependent on this fossilized sunlight, although a surprising number of people take it for granted. Since 1860, geologists have discovered over 2 trillion barrels of oil. Since then, the world has used approximately half. Before you can pump oil, you have to discover it. At first, it was easy to find and cheap to extract. The first great American oil field was Spindletop, discovered in 1900. Many more followed. Geologists scoured America. They found enormous deposits of oil, natural gas, and coal. America produced more oil than any other country, enabling it to become an industrial superpower. Once an oil well starts producing oil, it's only a matter of time before it enters a decline. Individual wells have different production rates. When many wells are averaged together, the combined graph looks like a bell curve. Typically, it takes 40 years after the peak of discovery for a country to reach its peak of production, after which it enters a permanent fall. In the 1950s, Shell geophysicist M. King Hubbard predicted that America's oil production would peak in 1970, 40 years after the peak of US oil discovery. Few believed him. However, in 1970, American oil production peaked and entered a permanent decline. Hubbard was vindicated. From this point on, America would depend increasingly on imported oil. This made her vulnerable to supply disruptions and contributed to the economic mayhem of the 1973 and 1979 oil shocks. The 1930s saw the highest rate of oil discoveries in US history. In spite of advanced technology, the decline in the discovery of new American oil fields has been relentless. More recent finds, such as Anwar, would at best provide enough oil for 17 months. Even the new Jack 2 field in the Gulf of Mexico would only supply a few months of domestic demand. Though large, neither field comes close to satisfying America's energy requirements. Evidence is now mounting that world oil production is peaking or is close to it. Globally, the rate of discovery of new oil fields peaked in the 1960s. Over 40 years later, the decline in discovery of new fields seems unstoppable. 54 of the 65 major oil-producing nations have already peaked in production. Many of the others are expected to follow in the near future. The world will need to bring the equivalent of a new Saudi Arabia into production every 3 years to make up for declining output in existing oil fields. In the 1960s, 6 barrels of oil were found for every one that was used. 4 decades later, the world consumes between 3 and 6 barrels of oil for every one that it finds. Once the peak of world oil production is reached, demand for oil will outstrip supply, and the price of gasoline will fluctuate wildly, affecting far more than the cost of filling a car. Modern cities are fossil fuel dependent. Even roads are made from asphalt, a petroleum product, as are the roofs of many homes. Large areas would be uninhabitable without heating in the winter or air conditioning in the summer. Suburban sprawl encourages people to drive many miles to work, school, and stores. Major cities have been zoned with residential and commercial areas placed far apart, forcing people to drive. Suburbia and many communities were designed on the assumption of plentiful oil and energy. Chemicals derived from fossil fuels, or petrochemicals, are essential in the manufacture of countless products. The modern system of agriculture is heavily dependent on fossil fuels, as are hospitals, aviation, water distribution systems, and the US military, which alone uses about 140 million barrels of oil a year. Fossil fuels are also essential for the creation of plastics and polymers, key ingredients in computers, entertainment devices, and clothing. The global economy currently depends on endless growth, demanding an increasing supply of cheap energy. We are so dependent on oil and other fossil fuels that even a small disruption in supply may have far-reaching effects on every aspect of our lives. Energy is the ability to do work. The average American has available the energy equivalent of about 150 slaves working 24 hours a day. Materials that store this energy for work are called fuels. Some fuels contain more energy than others. This is called energy density. Of these fuels, oil is the most critical. The world consumes 30 billion barrels a year, equal to 1 cubic mile of oil, which contains as much energy as would be generated from 52 nuclear power plants working for the next 50 years. Although oil only generates 1.6% of US electricity, it powers 96% of all transportation. In 2008, 2/3 of America's oil was imported. Most was from Canada, Mexico, Saudi Arabia, Venezuela, Nigeria, Iraq, and Angola. Several factors make oil unique. It is energy dense. 1 barrel contains the energy equivalent of almost 3 years of human labor. It is liquid at room temperature, easy to transport, and usable in small engines. To acquire energy, you have to use energy. The trick is to use smaller amounts to find and extract larger amounts. This is called EROEI, energy return on energy invested. Conventional oil is a good example. The easy-to-extract, high-quality crude was pumped first. Oilmen spent the energy equivalent of 1 barrel of oil to find and extract 100. The EROEI of oil was 100. As the easy-to-find oil was pumped first, exploration moved into deep waters, or distant countries, using increasing amounts of energy to do so. Often, the oil found now is heavy or sour crude and is expensive to refine. The EROEI for oil today is as low as 10. If you use more energy to get the fuel than is contained in the fuel, it's not worth the effort to get it. It is possible to convert one fuel source into another. Every time you do so, some of the energy contained in the original fuel is lost. For instance, There is unconventional oil, tar sands and shale. Tar sands are found mainly in Canada. 2/3 of the world's shale is in the US. Both of these fuels can be converted to synthetic crude oil. However, this requires large amounts of heat in fresh water, reducing their EROEI, which varies from 5 to as low as 1.5. Shale is an exceptionally poor fuel, pound for pound containing about 1/3 the energy of a box of breakfast cereal. Coal exists in vast quantities and generates almost half of the planet's electricity. The world uses almost 2 cubic miles of coal a year. However, global coal production may peak before 2040. The claim that America has centuries' worth of coal is deceptive, as it fails to account for growing demand and decreasing quality. Much of the high-quality anthracite coal is gone, leaving lower-quality coal that is less energy-dense. Production issues arise as surface coal is depleted and miners have to dig deeper and in less accessible areas. Many use destructive mountaintop removal to reach coal deposits, causing environmental mayhem. Natural gas is often found alongside oil and coal. North American discovery of conventional gas peaked in the 1950s and production peaked in the early 70s. If the discovery graph is moved forward by 23 years, the possible future of North American conventional natural gas production is revealed. Recent breakthroughs have allowed the extraction of unconventional natural gas, such as shale gas, which might help offset decline in the years ahead. Unconventional natural gas is controversial, as it needs high energy prices to be profitable. Even with unconventional gas, there may be a peak in global natural gas production around 2030. Large uranium reserves for nuclear fission still exist. To replace the 10 terawatts the world currently generates from fossil fuels would require 10,000 nuclear plants. At that rate, the known reserves of uranium would last for only 10 to 20 years. Experiments with plutonium-based fast breeder reactors in France and Japan have been expensive failures. Nuclear fusion faces massive technical obstacles. Then there are the renewables. Wind power has a high EROEI, but is intermittent. Hydropower is reliable, but most rivers in the developed world are already dammed. Conventional geothermal power plants use existing hotspots near the Earth's surface. They are limited to those areas. In the experimental EGS system, 2 shafts would be drilled 6 miles deep. Water is pumped down one shaft to be heated in fissures, then rise up the other, generating power. According to a recent MIT report, this technology might supply 10% of US electricity by 2050. Wave power is restricted to coastal areas. The energy density of waves varies from region to region. Transporting wave-generated electricity inland would be challenging. Also, the salty ocean environment is corrosive to turbines. Biofuels are fuels that are grown. Wood has a low energy density and grows slowly. The world uses 3.7 cubic miles of wood a year. Biodiesel and ethanol are made from crops grown by petroleum-powered agriculture. The energy profit from these fuels is very low. Some politicians want to turn corn into ethanol. Using ethanol to supply 1/10 of projected US oil use in 2020 would require 3% of America's land. To supply 1/3 would require 3 times the area now used to grow food. To supply all US petroleum consumption in 2020 would take twice as much land as is used to grow food. Hydrogen has to be extracted from natural gas, coal or water, which uses more energy than is generated from the hydrogen. This makes a hydrogen economy unlikely. All the world's photovoltaic solar panels generate as much electricity as 2 coal power plants. The equivalent of between 1 and 4 tons of coal are used in the manufacture of a single solar panel. We'd have to cover as many as 140,000 square miles with